Hey, physicists. So I promised you that we would go through these torque and rotation problems. Here's the first one. So I'm just putting these on separate pages just so it's a little easier to manage for me. So question one says, the engine in a small airplane is specified to have a torque of 500 Newton meters, and the engine drives a 2-meter long, 40 kilogram single blade propeller. Upon startup, how long does it take the propeller to reach 2,000 RPM? So there are a few pieces here. Just like any problem where you're not really sure where to start, best thing to do is follow the guess method and write down your givens. So I'm going to go ahead and do that, and you should follow along with me as well. So it says that there's a torque of 500 Newton meters. So I'm going to go ahead and write that down, 500 Newton meters. I like to write these givens, again, even though I can see them in the problem, because it helps me to kind of figure out how to attack the problem. The second part says the engine drives a 2-meter long, 40 kilogram single blade propeller. So the length of the propeller, it says, is 2 meters, and the mass of the propeller is 40 kilograms. And then it says, upon startup, how long does it take the propeller to reach 2,000 RPM? So I don't know if you know RPM. If you don't, let me introduce you to it. So RPM just means revolutions per minute. So I'm going to, instead of writing RPM here, I'm going to there we go, write this as revolutions per minute. And we can think about that then in terms of, okay, what rotational kinematics variable does this relate to? And revolutions can relate to radians, right? We can convert from revolutions to radians by saying that 2 pi radians is 1 revolution. And we can also convert from minutes to seconds if we want to. But when you see that, you're going to have radians per minute or radians per second. So hopefully that makes sense that then this is the final angular speed of the propeller. Okay, I am going to go ahead and convert this from minutes into seconds so that I can get a value in radians per second, which is what we usually use. So making that multiplication, I got 209.44 radians per second. I hope as you're working through these problems that you're writing them out, that you're doing them, that you're checking my math so that you know how to approach them. As I've said before, the AP exam isn't going to focus on problems with this much mathematics, this much computation, but going through the process helps you to see how to approach the problems. All right, so we know a final angular velocity. I think it says that it starts at rest, or it kind of implies it, so we know that the initial angular velocity is 0, which is also helpful, okay? And then we need to figure out what's going on. So the motor is actually getting this whole blade to spin. And I pulled from the chart that I had given you a couple of days ago, I think it's this one, with all of the different moments of inertia. I pulled the one that was most appropriate. So if you look carefully at this, you can kind of imagine that this is like a single blade propeller of an airplane. Okay, so it's one big rod that's being rotated through the axis through its center. And so we can also note that the moment of inertia for this object is going to be 1/12 the mass of it times the length squared. Okay, and again, you don't have to have that memorized. You don't even really have to know where it comes from. I just want you to know how to deal with the problems. Okay. And then finally, the last thing that we would do when we're starting to set up our guess method is to write down our unknown, and that is our time. So in order to find the time, it kind of implies that we're going to use some kinematics. And we've got initial and final angular velocity. So we need one more piece to the puzzle, and that's going to be our angular acceleration. Part of the hint that I have that we're going to do that is that we're given our torque. And we said a couple days ago that torque is equal to I alpha. So we can solve this for alpha. We could say that alpha is equal to torque divided by moment of inertia. We already know the torque, and we know an equation now for moment of inertia. So we can solve this fairly easily. So let's take a look here. So we've got alpha is equal to, so that's going to be our torque that we know, divided by 1/12 the mass, which is 40, times the length squared. The length is 2. We got to square that, okay? And when I plug these values in, I'm actually going to go ahead and throw all of this together in this problem. If you want to do it step by step, that's 100% fine with me. Um, but just I like to do algebra. So I've got my alpha, I've got my initial and final angular velocities and time. And I recall from my kinematics equation sheet that alpha is equal to omega final minus omega initial divided by time. Solving that for time, we've got omega final. Well, that omega initial is going to go away, isn't it? So I'm just going to get rid of it now. Get it out of my space here, divided by alpha. I can say this is omega final divided by, well, it's going to be divided by torque, right? And then this piece here, it looks like it's going to go up to the numerator. So we've got m, or 1/12 the mass times the length squared. Okay, and now I've got a whole bunch of stuff I know. All I need to do is plug it into my calculator. You go ahead and do that as well. When I plug that in, I got a time of 5.58 seconds. Hopefully that was helpful to kind of walk through that. And as I said on Friday, let me know if you have any questions as you're going